Hello again and welcome to our second acids and bases screencast on the Bronsted Lowry definitions. I'll put the page references on at the end of this video along with the questions I would like you to do. So if you hold on a tick, I'll be back with you. Okay, so what we have here is the reaction, really the dissolution of hydrogen chloride gas in liquid water. So we're bubbling this hydrogen chloride into a beaker of water. What we end up with is the chloride ion and this hydronium ion. I'll come back to the hydronium ion in a moment, but the thing I want you to pay attention to now, and why I coloured it in red, is this hydrogen. Now, the Bronsted-Lowry definitions are all about proton transfer. So give me a tick. So let's just remind ourselves of something quickly. A H plus is a proton in the middle. Sorry, let me just try and draw that slightly better. So a hydrogen atom is a proton in the centre, a single proton with an electron buzzing around the outside. But if it's a H plus, there's no electron. So a H plus ion is a proton. So I'll be using hydrogen ion and proton interchangeably. Our textbook does too, just something you need to keep in mind. Okay, so let's have a squiz at this this hydrogen ion, this proton here, and what happens to it, because what happens here is the key to what gets defined as what. So this hydrogen ion is being transferred over to this water, which means that we end up with a chloride ion on its own and a water that effectively has an extra hydrogen attached, which is what we see here. Now, Bronsted-Lowry says that, sorry, I'll type this because it's really important that you guys get this. Come on, type for me. So the thing that is donating is our acid. The thing that is accepting is our base. So in this reaction we have here, we have this hydrogen chloride donating a proton. So this hydrogen chloride is our acid. This water is accepting a proton, so it's a base. Let me just run through that again. Bronsted-Lowry is about proton transfer. The thing that is donating a proton in a reaction is called the acid. The thing that is accepting a proton in the course of a reaction is called the base. Remember, H plus and a proton are the same thing. Okay, let's now have a closer look at this hydronium ion, because we're going to be spending quite a bit of time with this. Okay, so we have our water molecule. That's where we started with our reaction. So we start with our water molecule. Now remember, our water molecule has, because of this oxygen here, 2 lone pairs of electrons up at this end, which is what gives it that tetrahedral structure. Now, what happens when we bring in our positively charged hydrogen ion. Now remember, those electrons have, these electrons up here, have that negative charge. So when we have that H plus coming in, and yes, I know I've drawn that H plus slightly bigger, but it doesn't really matter. That H plus is attracted to the negative charge here. So it ends up forming, effectively, why can't I erase those dots? It effectively ends up forming a bond here. It isn't exactly a covalent bond, but for our purposes, it's reasonably close. So in a hydrogen ion solution, the hydrogen ions aren't exactly roaming around freely. They find themselves being really strongly attracted to those electrons. So we end up with this structure here, which is usually shortened to H3O+. In chemistry, we will end up using the terms H3O+ and H+ interchangeably. Okay, now let's look at some questions. Now, there's only just a little bit of reading for this one, but our next section, I really needed to drill this Bronsted Lowry in because it's really the core of the rest of this topic. So if you do have any questions about this, please email me. I will get to my emails Friday and over the weekend. I will try and reply. If I need to, I will make another one of these screencasts to help you out over the weekend. So can you please make sure you read just that little section up the top of page 243 before you get to the acid-base conjugate pairs? That's our next topic. Okay, thanks guys.